Hello! Welcome to Pre-Calculus. Sorry, I'm feeling a bit sick today, so I couldn't come in, but we will try to make do with this sort of video format. We've been talking about parametric equations, and kind of the overarching theme for this unit is how are we going to use parametric equations to model different kinds of motion. So on Friday, on block day, we looked at oblique motion, if you have a ship sailing at a 12-degree angle, whatever, and vertical motion, if I drop something. How can we use parametric equations to keep track of the x-coordinate and the y-coordinate as a function of time? And that's basically what parametric equations do for us, right? They let us take x and y separately as functions of this third variable, time, or whatever it is, this unseen third variable. So our goal today is to look at how we can use parametric equations to talk about projectile motion. Projectile motion, you might have heard that term before. I've probably used it in class. In fact, I think we talked about this back in September when we were modeling with quadratics. If I throw a stapler through the air, and I want to keep track of its height as a function of time, or its x-coordinate as a function of time, how can we do that? And at the beginning of the year, we got some insight into that. Now that we have trigonometry and parametric equations, we can go a bit deeper. So if you could please take out the projectile motion student pages that the guest teacher passed out. Should be a nice thick packet. By the way, this is like all the worksheets that we're doing for the next few weeks. And they're all posted on Brightspace, so if you lose the packet, you can go print out another one. Also, all the answer keys are up on Brightspace, so you can check there for answer keys. So projectile motion student pages, let's look at number 1. We have a picture on a slow-pitch softball team who throws the ball toward home plate at a speed of 12 meters per second at an angle of 55 degrees with the horizontal. Suppose she releases the ball when it is at a height of 1.5 meters and when it is 0.7 meters to the front of the pitching rubber. Develop a set of parametric equations to model the position of the ball with respect to time. Okay, so you have a picture kind of like this, right? There's baseball at the, I'm like looking in the mirror here, at the 55-degree angle, it's going at 12 meters per second. So what does that tell us about speed in the components, the x and y components? If we're going 12 meters per second at this 55-degree angle, at what speed is the x value changing and at what speed is the y value changing? This sounds like vectors or trigonometry. Think to yourself for about 3 seconds. If we know the speed at this 55-degree angle, this 12 meters per second, how can we figure out the speed at which x is changing and the speed at which y is changing? Just think to yourself for about 3 seconds. Don't speak yet. Hey! Alright, now turn to the person next to you. How are we going to figure out the speed at which x is changing and y is changing if we know this 12 meters per second at the 55 degrees? I'm just going to sit here and wait for a few seconds while we talk. Okay, and back together. If I could have your eyes back up here, please. I wonder how this works with the video. I have no idea if this is working or not. Anyways, so we know 12 meters per second at the 55-degree angle. So to figure out the x and the y, we're looking for the sides of this triangle, right? The lengths of this triangle represent speed. So we can use some trigonometry here. For the x, we can use 12 times cosine of 55 degrees. And use sine for the y. So let me write this down real quick. So we got 12 times the sine of 55 degrees. For your y-axis, 12 times cosine of 55 degrees for the x. I'll show this on the screen in a second. 12 cosine of 55 degrees for the x. 12 sine of 55 degrees for the y. So you get these parametric equations, but there's some other things to keep track of as well, like the fact that the ball is starting out with an x value of 0.7 and the y value of 0.15. Oh, and by the way, notice here I have speed times time, that gives me the distance traveled, right? There's 12 cosine of 55 degrees. That's the speed in the x direction. Multiply that by time, now that gives me the distance traveled in the x direction. But if I'm looking at from the pitching rubber, I also need to add in this 0.07 meters and the 1.5 meters in the y direction. So let me stick those in. X plus 0.7. And in the y, we'll need plus 1.5. So something like that. Oh, but also, this looks like a straight line, right? These are oblique motion equations. If I throw this ball, it's not going to keep traveling along a straight line. I also need to keep track of gravity. At some point, this ball is going to come down. So we're in meters. This is the negative 4.9 t squared that we saw the other day. Let's add that in. So there are some nice parametric equations. In your x direction, your speed is 12 cosine 55 degrees. Multiply that by time to get the x-coordinate plus that 0.7, that's, the head start. For y, there's your speed 12 sine of 55 degrees. T gives you the distance traveled in the y direction. Subtract off the distance that falls because of gravity. Because basically there's two forces acting on this ball. It's the force that you get when you throw the ball, plus the force of gravity pulling it down. And then there's a 1.5 meters head start that it already had. And you can plug these into a calculator. You get x equals 6.88 t plus 0.7. And y is negative 4.9 t squared plus 9.83 t plus 1.5. So your parametric equations end up looking something like that. I'll give you about 15 seconds to finish writing these down. And also the answer keys for this are on Brightspace, so if you missed something during this video, you can go double check there. Oh no, my screen's fading out. Don't do that. I'm going to pause for a second and start a new video recording.